I have some fun news that after a couple of weeks of reviewing the material of Thermo 1, we are finally ready to delve into the topic of this class, which is phase equilibrium. We're going to start by talking about phase equilibrium for a single component. The question that is always I want you to have on your mind, and the main question of what we're trying to answer, is how can we accurately predict or model phase changes when no data is available? In other words, given a chemical, can we predict what temperatures, what pressures, phase changes will occur? How can we predict what phase the species will even be in? So if I give you ammonia, for instance, and say the temperature is T1 and P1, could you predict whether or not the ammonia is solid, liquid, or vapor? Of course, for many different commodity chemicals that have been studied, you will have data available to you oftentimes. But again, we are building towards being able to model these things for mixtures. And for mixtures, it's just simply not feasible to have every single mixture at every single composition have an experiment that describes that. So we need models and methods in place that we can predict this with mathematical equations and not just data. I want to start by posing a question to you. And it may seem a little bit strange, maybe you've never considered this before, but why do you think water is liquid at room temperature? Philosophically, you can say that it's a reason for life developing on Earth, because if water were a solid at room temperature, you can't develop life in that. And similarly for a vapor, it's hard to develop life. So water has to be liquid at the temperature that the Earth is. Or why does it boil at 100 C in 1 atmosphere? The smart aleck answer is because that is what the temperature, the people who made the temperature scale decided that 100 C was going to be the boiling point of water. But my point is that other chemicals boil at different temperatures. So what makes a chemical different in terms of what its boiling point is, and how can we accurately predict that? One way to start to try to answer this question is to consider that for a spontaneous process, remember Sgen must be greater than 0 of the universe in a spontaneous process. Okay, so you could go and look up what the enthalpy of a liquid is, a liquid water, for example, and compare it to the enthalpy of a liquid vapor. What you would find is that the enthalpy of a vapor is greater than the enthalpy, the entropy of a vapor is greater than the entropy of a liquid. So given that information, so if this is true, why isn't all water vapor? Right? That would seem to make sense, that if the entropy of the universe is continuously increasing, then why wouldn't all water on Earth be vapor instead of liquid? Because that would be the higher entropy state. And the answer to that is that while entropy is greater for a vapor than it is for a liquid, it's also true that enthalpy of a vapor is greater than enthalpy of a liquid. In other words, to get to this high energy state, that energy has to have come from somewhere. So in the case of boiling, or in the case of increasing temperature and boiling, some amount of heat has to be added, or some amount of energy has to be added from the environment to the molecules to get it up to that higher energy state. Sometimes it can come from the rest of the molecules themselves. So the energy that's contained within a system can be used to increase the enthalpy of the system. We can look at some other thermodynamic properties that all increase upon vaporization. So beyond entropy and enthalpy, also internal energy of a vapor is greater than the internal energy of a liquid, and the specific volume is greater for a vapor than the specific volume of a liquid. So therefore, because all of these properties increase, it's not really useful to use them as a method to predict whether or not a phase change operation will occur. Now, there is one property that does not increase upon a phase change, and that is the Gibbs free energy. So remember that the Gibbs energy is defined as enthalpy minus T times entropy. So for a given process, if enthalpy increases, but S also increases and temperature increases, it's hard to say whether or not Gibbs free energy increases for a vapor or for a liquid. So if I compare Gibbs free energy for a vapor, it's unclear whether or not it's less than, greater than, or equal to Gibbs free energy for a liquid. Now, furthermore, Gibbs free energy is the only natural function of T and P. So in the fundamental property relationships, I derived this a couple of class times ago, we could say that dG is equal to V dP minus S dt. So this is what I mean by a natural function of temperature and pressure. So for changing of temperature and changing of pressure, those are the independent variables of this dG function. But we also know that for a phase change process, pressure and temperature are the same. In other words, if you're heating a pot of liquid water, the temperature will increase until you get to the boiling point. Then the phase change will occur at constant temperature. Remember from your high school chemistry classes, temperature and pressure is constant until the phase change is complete, and then temperature can increase. So for a phase change operation, dP is 0, dt is 0. And therefore, we come to an interesting conclusion that for a phase change operation, there must be no change in Gibbs free energy. So from this, you can infer that at equilibrium, the Gibbs free energy of the vapor will be equal to the Gibbs free energy of the liquid. We will call this the equilibrium criterion. In other words, if this is true, we will have a phase change in the form of equilibrium. Now, what if there is not phase equilibrium present? Can we predict which phase would be present? And the answer is yes. The way you would do this is you would start with the definition of Gibbs free energy. So you'd say that Gibbs is equal to enthalpy minus T entropy. And for a given temperature, you can, and pressure, so you'd have to know two thermodynamic variables in order to set the system. You'd have to know temperature and pressure. You could then look up enthalpy and entropy, calculate what Gibbs energy is for the vapor, liquid, and solid phases, and whichever one is minimum will be the phase that is present. So you can derive that by considering a closed system that is at constant temperature and by simplifying the energy and enthalpy balances. So we'll assume no kinetic potential energy changes, and we'll also assume no shaft work, but we're not going to say that there is no expansion or contraction work. So the energy balance simplifies to du dt is equal to work from expansion compression plus Q. This is, of course, the differential form of the energy balance, not the integral form. The entropy balance in the same differential form is ds dt is equal to, this would be the sum of Q over T, but because it's a closed system, we'll say there's only one energy flow plus S gen. And then in the derivation, we're going to solve the entropy balance for Q and then plug that into the energy balance. So solving entropy balance for Q. See if you can solve it before I do. Q is going to be equal to T ds by dt plus T times S gen. Minus S gen, sorry. And also the T can go in or outside of this derivative because it's constant anyway. So it's a constant temperature, it can go inside or outside the derivative. Now I'm going to plug this expression into the energy balance. Plug this Q into energy balance. And that is going to give me, du dt equals work, expansion, contraction, plus dTs. So I'm going to put it inside. dTs by dt minus Ts gen. Oops. Now the expansion contraction work I can express as minus P dV dt. And now I can group all the dt terms together. So I'm going to bring these two terms over to the other side such that I can say du and then plus P dV I'm sorry, the D's can get grouped, so it's U plus PV minus TS all by dt is equal to minus TS gen. And finally, I can say that U plus PV is H, in which case I can say that H minus TS is equal to G. So finally, I can say that dG dt is equal to minus TS gen. So where does this get us? Remember that for a spontaneous process, S gen is going to be a positive number, and T, when expressed on an absolute temperature scale, will also be a positive number. Therefore, dG dt is always less than 0 for a spontaneous process. And Gibbs free energy is always decreasing. It's kind of like the opposite of entropy in that respect. Entropy always increases, Gibbs free energy always wants to be a minimum. So that is how, this is just the derivation that allows me to say this. That allows me to say that the phase that is most likely to exist will have the minimum Gibbs free energy. That is, I think, a sufficient introduction to some of the principles that we'll be talking about in this chapter. I'm going to have one more video today, and that is going to be an introduction to the Clausius-Clapeyron equation.